Okay, welcome back. Happy Wednesday. Today is our 18th class of the semester. We are covering section 1.5. By virtue of being back in chapter 1, this is another pre-calculus review day. Today we're talking about trigonometric functions. No calculus today, just reviewing pre-calc. Coming up on Friday is our project check-in day. You will want to be as close to on target with my recommended calendar for both projects as possible coming into Friday's class. I'll have no agenda on Friday. You're just going to come in and work with each other on the projects, or work with me on the projects, or work on your own on the projects. And then coming up Monday, we're going to do derivatives of trig functions, following up on today's review of trig functions. Also on Friday, I'm going to hand you a take-home quiz. Questions on the calendar? 24. Okay. All right, so let's go ahead and get started here at the top of page 24. Our daily summary. Today we review trig functions so we can find and use derivative formulas for them next class. Number 1, remember the way to convert between degrees and radians is to use a particular identity. I'll fill this guy in, 180 degrees. How many radians is that? That is pi radians. And so if you want to go back and forth between degrees and radians, you're either going to multiply by 180 over pi or pi over 180. Both of those fractions are equal to what magic number? 1, right? Okay, in calculus, we assume radian mode unless otherwise noted. I repeat, in calculus, we assume radian mode. This is going to be troubling for many of you in physics because I think a lot of physics is done in degrees. And so if you are coming from Ted's class, you might have been in degrees, and if you're heading to Ted's class, I want you in radians here, and then make the switch when you switch to physics. All right, there's a very good reason why calculus prefers radian mode, which will become clear during Monday's class. Okay, number 2, let's recall some facts about functions of this form. I'm actually going to make a small change here. See that x minus c, can you make it a plus? Same thing in the other equation. Let's make them both pluses. Okay, so we've got these two big functions, a sine of b, x plus c plus d, and then the same thing with cosine. We're going to call them both sinusoidal functions, even though one of them is cosine. And so we just want to remember some of the basic stuff about what the effects of a, b, c, and d are. You guys know very well the graph of sine of x and the graph of cosine of x, and we should be able to transform them by putting these 4 constants, a, b, c, d, in the various places. So let's run through. Amplitude, remember amplitude is how far from the middle. It's also a vertical stretch. What letter? A. Are you okay with that? One little detail here. If a happened to be like -3, would you say the amplitude is -3? What would you say the amplitude is? Is 3, right? So then if I'm being really precise, absolute value. So I'll put absolute value there. Okay, the horizontal shift. What letter is the horizontal shift? It is C. It's that guy right inside the parentheses. I changed the minuses to pluses. It doesn't make any difference whether it's minuses or pluses, but you need to know how to tell whether the shift is left or right. And so we're not going to review, like it depends on whether C is positive or negative, but you'll figure it out if you don't already have those things memorized at the moment. The period is actually not one of these 4 letters, but it's related to one of the 4 letters. Which one of the 4 letters affects the period? It's B, and normally the period of sine of x is what? Not pi, but 2 pi, right? If a complete cycle of the sine function happens over the horizontal distance of 2 pi. But that B has the effect of either smushing or stretching horizontally, and 2 pi over b is the new period. Okay, and then midline. So again, just think of sine of x. What's the midline for sine of x? It is y equals 0 is the x-axis. But if we shift vertically, then that midline shifts. Which letter is that vertical shift? D.
It's definitely A.
So the negative of the absolute value. Right, so D, either up or down depending on the sign of D. You'll figure it out. What I'm really interested in is that you're able to handle problems like this one. So let's give this a shot, number 3. A rabbit population varies sinusoidally between 3,000 and 5,000 rabbits. The last 2 times the population reached 5,000 rabbits were in 1990 and 2000. We're going to model the population of rabbits as a function of t, which is going to be the number of years since 2000. Okay, so for me, in order to make some headway here, I need to plot a few points and draw my graph, and then I can find the equation. Okay, so I have information back in 1990. Now, if t is the number of years since 2000, then what value of t is 1990? Is it 10? Is it negative 10? Okay, so we're coming out here to negative 10, and what was the population? Was 5,000. So we're up here at 5,000, and I've got my first point on my population curve. And it says the population was 5,000 again in the year 2000. What value of t is the year 2000? Is 0, because t is the number of years since 2000. So that means my next dot is up there, right there on the y-axis. And then pretty much the only other info I have is what? Goes down to 3,000. Okay, so this is not to scale, but 3,000 is here. When? When does it hit 3,000? At -5, right? So we know it's halfway in between. And so definitely right there at -5. And armed with those 3 points, knowing that there's some maxes and a min, I can draw a curvy thing that hits these points, right? Something like that. So that's one period. Obviously, there's many, many periods, but all we need is one. Okay, let's see if we can start figuring out the values of A and B and C and D. Those are the 4 things. Once we have the 4 things, we'll just shove them back into our equation and we're done. Okay, let's start with D. D is the vertical shift or the midline. What is it? It's 4,000, right? We're looking for the middle, not the new top, but the middle. Middle. So the middle is there at 4,000. Let's now move to the amplitude A. The amplitude is the vertical stretch. It's how far from the middle to get to the top or bottom. What is it? Is it 2,000? It's how far from the middle? It's 1,000, right? 1,000. How far from the middle to the top or the bottom? 1,000. Okay, that's fine. All right, let's move to C. C is the horizontal shift, sometimes called the phase shift. We need to decide how far left or right this sine or cosine function has moved. Now we're free to call that a sine or a cosine, and we can pick whichever one. What do you guys think? If we say cosine, then the horizontal shift is 0. And so that's why we're going to say cosine. We see that? Because cosine we know normally, so we'll draw here. So there's like a sine function, right? And then cosine normally starts up there at the top. And this guy right here is starting at the top. I use the word start kind of in quotation marks. It's cosine. Yeah, cosine starts up there at 1 and then comes down. Yeah, and so I think we can think of that as cosine because it's right up here starting at the top, ready to begin a cycle, right? So if we think of it as cosine, then we can just call it 0 if we use cosine. But just for practice, let's also think about what it would be if we used sine, like if we were forced. Like if some big mean calculus teacher said you have to call this a sine function, let's see if we can figure out what the horizontal shift is. So sine over here in blue normally, quote unquote, starts at the origin and it's on its way up. So I'm going to look over there and I'm going to try to find that point in that cycle where it's in the middle heading up. Do we see it? Is it -5? -2.5. It's this guy right here. That's the only spot. It's in the middle on its way up. What's wrong with this point over here? Yeah, it's in the middle, but it's heading down. which would be fine if we called it negative sine. That would be okay. But if we wanted to use sine, we have no choice. We have to pick that point right there. So that point clearly is halfway. So that's a negative 2.5. And so then I'll put over here, or negative 2.5. Yeah, whether it's positive or negative depends on, remember the minus sign that I changed to a plus sign in the formula? Yeah, so like, I don't know what it is. It depends on what version of the formula we use. So at the moment, I'll just call it negative 2.5, and we'll write the answer and make sure we get the right sign in a minute. Okay, and then finally B. I've got a B equals. B actually requires some calculation. So B is related to what characteristic of the curve? Is the period. So the first thing we need to know is the period. So the period, just by looking at it, is how much? 10. Right, that's how long for a complete cycle. So the period is 10. And I wrote a formula up there that B is 2 pi over the period. Well, going the other direction, wait, is that what I wrote? I wrote the period is 2 pi over B, but it also is true that B is 2 pi over the period. Those two equations are equivalent. And so we take 2 pi and divide it by the 10 that we got. So pi over 5, that's our B. Okay, so I think we're ready to just smush it all together. So now again, we're going back to our original equations with the A, B, C, D in the spots that they're in. So our final answer here, we can call it, what are we doing here? We'll call it Y. Okay, so the first letter in our equation is A, so we go 1,000. Did we use sine or cosine for the 0? We use cosine, so let's use cosine. Okay, and then what's the next letter? It's a B, so we do pi over 5. Now it's really important, the next symbol that we write is, before we write the X, it's parentheses. Make sure you see that in that formula, the B has been factored out. Okay, I think it was X up there, but it's T in this equation, so we'll use T. And then plus the C value, which is how much? 0. Close, close. And then finally, plus 4,000, shifting the whole thing up 4,000. Okay, so there's our equation. Pi over 5 times T. Yeah. Okay, so that's one version of things. Let's go ahead and write down the sine version as well. Okay, we still start with the 1,000. We're going to now write sine instead of cosine. It's still a pi over 5. And then we do T, and then I'll leave a little space here, and then plus 4,000 at the end. Okay, so all we have to do is get the sign right for the number that we're putting in there. It's kind of confusing sometimes to talk about this stuff because I said we're looking to get the sign. I'm talking about the sign of the number 2.5 as opposed to the sign graph that we're talking about here. When I talk about the sign of a number, how do we spell that? Spell the word sign when we mean sign of a number. It's not a trick question. How do we spell the word sign for sign of a number? S-I. For the sign of a number is S-I-G-N. Yes? Sign of a number is S-I-G-N. But sign, the trig function, is spelled, it's 4 letters long. How do you spell? S-I-N-E. They sound the same, but they're spelled differently. So the sign of a number, S-I-G-N, the word sign is an abbreviation. Does anybody know what it's an abbreviation? Sinus is the sign function, S-I-N-E. But I'm talking about the other one, the S-I-G-N. It's a shorthand version of the word signature. The signature of the number is either positive or negative. Okay, so we just have to get the signature of that 2.5 correct in the blank parentheses here. Okay, so I have to really slow down whenever I do this kind of thing. Normally, my sign function would start in the middle and go up. I am trying to take that normal sign function and shift it which way? To the left. I really have to slow down and do that carefully to make sure I know which one is coming from the other. And so if we're shifting left, what kind of a number do you want? It's a positive number. So we're going to put a plus 2.5 in there, which I think is what Lex was talking about. When I wrote negative 2.5, I guess my negative was with the minus sign still built into the formula. Yeah. Okay. Yeah, Nick.
It's kind of confusing when I took you can get to the left there with the function like that where it's like repeating.
Yeah.
It would also be the same, right?
So you could move it to the right, absolutely. Let me see here. I'm gonna have to erase this after I draw it, but yeah. So like if we imagine this our R curve continuing, and again we're looking for the point now on that blue thing where it's in the middle and on the way up. Do we see it? In the middle and on the way up is this guy, and so this number, yeah, let's say 5, 7.5. Is that all right? And so another option, according to Nick, yeah, now we're taking the original green sign guy and we're shifting it right 7.5. So that makes it a T. A T what? Minus 7.5. Yeah. So now you're going to feel a lot of pity for me because I have to grade quizzes and tests where there are how many right answers? Infinitely many right answers. And I have to check all of them. You could. I appreciate that. Yeah. Yeah, tangent and cotangent have the same kind of relationships there. Yeah, I mean, with all these trig functions, there's infinitely many right answers to the equation. Yeah. So you imagine how long my answer key is when I'm writing the key, right? Okay. All right, so that's fine. Part B says, during what year and month will the rabbit population next be 4,500? We're going to answer this question in two ways. First, we'll do it algebraically, and then we'll do it with a graphing utility to check our answer. Okay, so let's do this algebraically. So the 4,500, is that a value of t or y? That's a y. So all we're going to do is either pick the green equation or the orange equation and make the y 4,500. Which one do you want to pick? Green is easier, right, because of the t plus 0. Okay, we're going to pick the orange. 4,500 equals. I didn't say you get to pick. I just wanted to know which one you picked wisely. But let's make sure we can handle the tougher one too. So according to the orange, 1,000 sine pi over 5 t plus 2.5 plus 4,000. Okay, what's the first step? Subtract the 4,000. So 500 equals 1,000 sine pi over 5 t plus 2.5. Next step. Just divide by 1,000. We'll reduce immediately, so we get 1/2 equals sine pi over 5 t plus 2.5. Okay. What do we do algebraically to both sides right now? Arc sine, also known as, let's say, other inverse sine, right? Arc sine or inverse sine, either way. So let's go ahead and write that symbolically, and then we'll do the calculation. So symbolically, you can either do this thing that looks like sine to the -1. You could also write that arc sine of 1/2. And that cancels the sign on the right-hand side. That was the idea. Okay, and this is the place where you might type the thing into the calculator, right? An inverse sine of 1/2. But it happens that 1/2 is one of the few numbers that we can actually, that we actually know, like without the calculator. Yeah, so in degrees, I think I heard a couple people say 30. That's true. Sine of 30 degrees is a half, but remember in calculus, we are in radian mode all the time. And so pi over 6 is good. So pi over 6 equals pi over 5 t plus 2.5. Okay, is pi over 6 the only answer to that left-hand side? How many answers? How many angles have a sine of a half? Infinitely many. Yeah, just keep going around. But I would say that between 0 and 2 pi, there are two fundamentally different angles that have a sine equal to a half. Yeah? So it's not enough to just say pi over 6 and then keep adding 2 pi's, continually landing on pi over 6. There's another one. And we need to know what the other one is because we're looking for a specific one. What did it say the first time after 2000, I think? What did it say?
When will it be?
When will it next be? Yeah, so we're looking for the particular one, and maybe it's one of the pi over 6's plus the right number of 2 pi's, but maybe it's the other one, and so we need to know the other one. So real quick detour into your group activities here. You guys recognize this guy, right? So let's fill in this first thing here. This first angle, that guy, how many degrees? 30. Put that in the first blank. In the next blank, it's the radian version of that same angle, pi over 6. And the next blank, it's the coordinates. What is the x coordinate at that spot? 3 over 2, comma, 1/2. That's good. And it's the y value that we know is the sine of the angle, right? So that's the half we were looking for, which is why pi over 6 was one of our winning angles. Where's the other spot on the entire circle where the y coordinate is a half? Do you see it? Is it pictured or do I need to scroll down? It's the mirror. It's over there. It's not the one down below. We want the y to be positive a half. There are places down below where the y is negative a half, but those aren't going to work for us. So we want the mirror. How many degrees is this mirror guy? 150, right? It's the 180 minus the 30. Okay, how many radians? 5 pi over 6 is good. What are you looking at over there? All right, 5 pi over 6 is good. The coordinates here, x is negative root 3 over 2, right? And the y is also 1/2. Okay. So when we were looking for an angle whose sine was equal to a half, we found one of them at pi over 6, but where's the other fundamental one? It's 5 pi over 6. So we need to write that equation as well, right down here. Or 5 pi over 6 equals. Okay, so we can solve each of these equations here for t. The rest of this is fairly straightforward. First thing we do is what to both sides? Divide by pi over 5. Let's make our lives a little bit easier. Multiply by 5 over pi, yeah? And then what happens with those pi's? They cancel. So what's left? 5/6. That's good. Equals t plus 2.5. And then over here, again, multiply by 5 over pi. And what do we get there? 25 over 6 is good. All right, just because we got all these fractions floating here, let's change this guy to a 5/2. I think that'll make it a little bit easier for us. And then we'll get our answer. So that 5/2 becomes how many sixths? 15/6, which gets subtracted over there, leaving negative, am I right? Negative 10/6, is that okay? Minus 15/6 from both sides. Same thing on this side, subtract 15/6 over here, what do we get? 10/6. Okay, so I think that's good. Might as well reduce. So that's 5/3, and that's a negative 5/3. All right. And so I guess that means just in terms of like years, this is 1 2/3 of a year, right? And that's negative 1 2/3 of a year. Remember, T was measured in time since when? 2000. So let's interpret this question to mean when is the next time from this moment right now when the population will be 4,500. This positive 1 2/3, in what year did that happen? 2001, right? This is years since 2000. So that's 2001 2/3 of a year. And then in this other guy, it's back in 1998 sometime. Okay, so let's progress forward. What do we add to get to the next corresponding numbers? Not 2 pi in this one. In this example, what do we add to get from one point to the corresponding point on the next cycle? Oh, yeah, what's the period for our function? The period for our function? So pi over 5 was the b, but that wasn't the period. 10, right? Full cycle happened over the course of 10 years. So we just get to keep adding 10s until we land on a number that we need, that we like. Right? So add 10 to this guy, we get to 2011 and change. Add another 10, you get to 2021 and change. But adding 10 to this guy maybe will give us the next moment when it happens. So we add 10 to this one, we get 2008 and something, and then 2018 and something. So I think this is our winner over here. So add 10 and then add another 10, and we get, what do we get, 18 1/3? Which means 2018 and then a third of the way through April. Do that right with the, right, are we in 2018 there or 2019? Yeah, so like if we just say t equals 1, then we're at the start of 2001. Yeah.
You're almost taking it 2 years.
Yeah. Yeah, I think that's good. Okay, and then I said that we would check our work here graphically, so you don't need to do this, but real quick, we'll just verify that our answer is solid. Can somebody read to me the function that we had, 1000 sine pi over 5, and then x plus 2.5, close, plus 4,000. Okay, before I hit graph, what do I need to check right in here? Radians. My calculator is always set to radians, but yours might not be. And you're going to get ridiculous answers if you don't check this. So anytime you hit one of these 3 buttons, sine, cosine, tangent, you first check the mode. Okay, so you could graph it, but that's kind of fruitless because what? It's way off the window, right? This is minus 10 to 10. That's no good. So how about we look at just the one period we were interested in our graph. It was negative 10 to 0, and then 3,000 to 5,000. I don't know, we'll go up by like 500s here or something. And we hit graph. And for me, I'm just like really picky about my windows, not like a grading wise, but just me, like I take personal pride in finding a nice looking window. And so like every every sine or cosine graph that I graph looks exactly like this, in that it always starts in the top left corner and then bottoms out in the middle and then ends in the top right. So it's kind of silly in that it always looks like that, but it does confirm to me, yes, the picture that I drew is the one that's up here. Okay, so that's fine. And then if we wanted to get to the 2018 that we're interested in here, how far should we go? Yeah, 18 and change. I'm going to go out to 20. No, it won't be perfect, but that's okay. And so we're looking for a place where the, but come on, look, that's nice up there. Top right corner. It's the little things. Okay, and we're interested in when this thing is 4,500. Was that the right number? Yep, okay, and so we're going to see this horizontal line shooting right through. How many solutions do we see on this window? 1, 2, 3, 4, 5, 6 is good, and the very next one I think is this one over here, right? And that's what we want. And so I think you guys have done this before, but second calc, and then which one will find me a solution point? Intersect, right? Number 5. And it says first curve, and you hit enter, and it says second curve, and you hit enter, and then all you got to do is scroll until we get close to the point that we want, which is this guy out here. And we hit enter, and it tells me 18.3333, 18 and a third. Okay, so I want to just do a tiny bit of the group activities together because there's some very sort of mundane things in the group activities that are a review, but I don't want them to slow people up. So we're just going to zip through the boring stuff and let you do the interesting stuff at your table. So the unit circle, we're not going to fill any of this in now. And in fact, I don't encourage you to spend your class activity time filling it in, as long as you understand what we just did there. I guess just one other number will be sufficient. What's this number right here? Yeah, pi over 4 is the angle, and then the x value is root 2 over 2, which is the same as the y value. And so like every other number here, I guess that's a 0 and a 1, like every other number there is either root 3 over 2 or root 2 over 2 or 1 over 2. And then zeros and ones on the extremes of the circle. Yeah. Mm-hmm.
I know, I understand why we use pi, the fractions.
How to get the 5 pi over 6. So there's a couple, or the pi over 6. Yeah, there's a couple of ways. So if you just want to convert 30 degrees or 150, maybe it's better to do the 150. So if you just want to convert 150 degrees, you just need to multiply it by the right fraction, and the right fraction is pi over 180 because pi radians is exactly equal to 180 degrees. And so then it's just a matter of reducing. And so like you can divide by 10 and get 15 over 18 and then reduce out the 3's. And what do we get? 5 and 6, right? So that's just sort of the brute force way. I think there actually is a much cleaner way to do this. Well, I don't want us to get too distracted here, but really quick. If I look at half of 30 degrees, that's 15. If you take 15 degrees and you play the same game that we did up here, you get pi over 12, okay? Okay, so we've got all these crazy patterns here, pi over 6, pi over 4. What's the next one? This is a pi over 3 here. Like, it's just complete chaos in terms of like the numbers. The next one up here is pi over 2. Right, pi over 6, 4, 3, 2. I'm a math guy. I look for patterns. I don't see any there. But there are patterns there, and we just don't teach them. Take a look at the 15-degree angle, which is not marked, but it's there. We said this was pi over 12, right? Okay. Every single angle I'm going to be talking about is going to be just multiples of that 15 degrees. We're just going to keep going up pi over 12s. So the next one is 2 pi over 12, yes? The next one is 3 pi over 12. Next one, 4 pi over 12. The next one we don't care about, but we're going to mark it. 5 pi over 12. The next one, 6 pi over 12. Clear patterns there, right? But then we reduce, and we completely lose the fact that they all came from just pi over 12s. Right? This guy reduces to pi over 6, pi over 4, pi over 3, pi over 2. Okay. So that's the underlying. Yeah, the 5, nobody cares about it, I'm sorry. Yeah, so there's why these fractions look like they have no patterns, because they've been reduced. So this is an alternative to doing this this conversion. Let's just say, oh, how many pi over 12s am I? Okay, so I encourage you not to fill in the unit circle during activity time today. There's nothing to it. Down here it says on the unit circle, sine of t is the y coordinate. Right, we kind of use that today. Cosine of t is the x coordinate. Again, we're on the unit circle, so in theory these are both. It's really a y over 1 and x over 1. It's divided by the radius of the circle. Tangent has both letters. Just got to get them in the right order. Y over x is good. And then the three sort of neglected trig functions. They're easy if you match them correctly. What's this first one? 1 over y. And the next one, 1 over x. And then, yeah, so don't use the word inverse, but sine and cosecant are the ones that are reciprocals of each other. And cosine and secant. Yeah, you want cosine and cosecant to go together, and they do go together. They just don't go together in this way. They don't go together in the reciprocal way. They go together in some other way, which we don't need to get into. Okay, on the next page, those are interesting questions. Down here, number 4 is the boring one. We'll do it together real quick. In a right triangle, using opposites, adjacents, and hypotenuses, sine of t is opposite over hypotenuse. I don't know if you guys remember this sort of made-up acronym, SOHCAHTOA, which is great as long as you know how to spell that word, but if you don't, then yeah. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then again, as long as you put the other 3 in the right spots, it's all reciprocals. So hypotenuse over opposite, hypotenuse over adjacent, and then adjacent over opposite. Number 5 is interesting. You will do that together. Number 6 is boring. It's just pictures of our 6 trig functions. So there's nothing to do on 6 other than to just refresh your memories and know that this resource is here for all 6 trig functions. One thing I just want to point out, the period of sine and cosine we said is 2 pi. By virtue of being reciprocals of sine and cosine, the periods of cosecant and secant are also 2 pi. But tangent has a period of pi. It is shorter, it's half. And therefore cotangent is the same pi, okay? So everything that we did, remember the 2 pi over b that we did earlier today? That's good for sine and cosine, but it's no good for tangent, right? For tangent is pi over b. Is tangent not? Yeah, yeah. I mean, you still run around the circle, but you repeat the values before you get to 2 pi. You repeat the values when you get halfway around the circle. Yeah. It doesn't actually hit at the pi's, or at some, maybe the pi over 2's in this case. But for sure, we can say the period is exactly pi, because if you pick a point and you want to find its partner point, they are exactly pi apart. Okay, on the next page, 7 is interesting, 8 is boring. Let's do 8 here. 8 are some quotient identities that, some of which we talked about today. I guess we didn't actually talk about these. Another version of tangent is sine over cosine. You've seen that. And then cotangent is the reciprocal. Cosecant is the reciprocal of sine, and secant is a reciprocal of cosine. And the way I remember that is that, as Nick says, it's not the way I want it to be. That's what I remember, is that it's not the way I want it to be. Okay, Pythagorean identities. One of them is sine squared of t plus cosine squared of t is 1 for any angle t. There are 2 other Pythagorean identities. I can never remember them, but it takes like 10 seconds to derive them, to create them from this equation. If you divide everything by cosine squared, sine squared over cosine squared is what? That's tan squared, right? Sine over cosine is tan, plus cosine squared over cosine squared is 1 equals 1 over cosine is secant, right? And then that's squared. So there's another.
The preferred way, I mean, I guess right now.
Okay, and then just as well, you could create another identity by dividing everybody by sine squared. Okay, first thing, sine squared over cosine, sine squared over sine squared, 1 plus cosine squared over sine squared, cotan squared, equals 1 over sine squared, cosecant squared. So those are the three. I only know one, but I know how to build the other two quickly. Okay, so I think we've done all of the boring review type stuff in the activities. Go back to the beginning of the activities, skip over all the boring review stuff and just do the interesting things. So go find that unit circle and skip it and just do the problem right below, okay? I'll walk around